Okay, so we're actually going to continue a little bit with intro to rotations. We talked yesterday about the velocity, the angular velocity, and the regular velocity as well. So we learned yesterday that while the angular velocity of a rotating object is what at all points? Is it the same at all points or different at all points? This is the angular velocity. It is the same at all points. Because remember, the angular velocity is based off the angle change. And no matter what point we're at, the angle change is still the same. So angular velocity at any point on a rotating object is the same, while the regular velocity is different. And again, usually they don't say regular, they just say velocity versus angular velocity. So keep that in mind. If they just say velocity, they just mean normal meters per second velocity. So if this is the case, how can we find the kinetic energy of an object if the velocity of that object is different depending on where you're looking at on that object? So we have this concept called rotational inertia. This tells us how the mass of a rotating object is distributed. It comes a bit from calculus, from doing the summation, basically, of a bunch of very, very little pieces. If we were to chop up that object into a bunch of little pieces and kind of adding it all together, that's where this comes from. Now, rotational inertia depends on the mass of the object, because again, it tells us how the mass is distributed, as well as the distance from where we're rotating. So this is I for rotational inertia. We try to write it kind of like an I with the dashes across the top so we can differentiate it from like an L. But this is the formula for rotational inertia. This is not on the AP Physics formula sheet. That rotational inertia I equals mass times the distance from the axis, r, squared. However, the kinetic energy for rotation is usually how they write that, K rotation. This is on the formula sheet, and I'm sorry, I meant to change that. That is I used a different font here, so let's add little there we go. So this is 1/2 times the rotational inertia times the angular velocity squared. Remember, that's the variable omega for angular velocity. Now, because rotational inertia has its own formula, you could also write this way, 1/2 and then replace with the formula for rotational inertia. Depending on the question, we will need to keep that in mind. Sometimes they say the rotational inertia is this, and then we know all of this because, again, this is the rotational inertia. It tells us how the mass of that object is distributed as it's rotating. So keep in mind, we can look at this two different ways. If we know the mass and we know the distance from the center, we can kind of plug it in like this. If we know rotational inertia right away, if they tell us that, then we can just go straight to plugging it in here, but you'll see that in the examples. So this is the kinetic energy. And again, it does look very similar to our normal kinetic energy formula. It's just that we have angular velocity, right, which is based on the angle. And again, this rotational inertia concept, but there's mass right there, right? Normally, this is our kinetic energy formula. So mass is still a thing in there. Speed is still a thing in there, but it's just angular now. So let's try some examples. That's actually it. All we got to do from here is really do some examples. I just realized. Okay, so looking at these examples here, once again, we have a wind turbine because that's a really easy example to use. The blades have a combined rotational inertia. So basically, again, if we're looking at the blades as a whole, So the mass of all of those blades, kind of. This is the rotational inertia as a whole. So again, keep in mind, this is the I. That's all of I. That was calculated by doing mass times the distance from the center squared, but that is it. That's I. So the blades make 4 complete revolutions every minute. What is the rotational kinetic energy of the blades? So we want to pay attention to what they're asking us to find here. They're asking us to plug in to the kinetic energy for a rotating object. So we are going to need to plug in here. Now, again, we have I. This is I. In order to get the kinetic energy, though, we do need to know the angular velocity. So I want you to look back to your notes from yesterday. Figure out what the angular velocity is in radians per second. In order for this formula to work, it has to be in radians per second. Look back to your notes, go ahead and give it a shot. Okay, so we're gonna have to do some conversions here, right? Because we have that it completes 4 revolutions every minute. So this is the start of 4 revolutions every minute. This is what we have to start with as the angular velocity, but we need to convert it to radians per second. So if you recall, 1 revolution is 1 travel around the edge of the unit circle. So there are 2 pi radians, because that's the circumference of a unit circle, per revolution. So hey, boom, boom, that's the whole point. Whatever I want to cancel out, we put it in the opposite position, right? So since revolutions was on top, I put revolutions on bottom, and then I put what I wanted on top. So that's our first conversion. And then we need to have seconds on the bottom. So I'm going to put seconds on the bottom. And what I want to cancel out is minutes here. So I'm going to put minutes on the top. So that means 1 minute has 60 seconds. So here's my conversion. Now I have, come on, radians over seconds. Go away. Go away. There we go. I have radians over seconds. So we just plug this in the calculator. So we got 4 times 2 pi. Where is my pi? And then divided by 60. Boys, shush. Okay, so we should have gotten an angular velocity of 0.42, we'll say, radians per second. Again, that was 4 times 2 pi, and then divide by 60 on the bottom. So now we have all the information we need. Again, we just gotta be careful that we always need to be in radians per second in order for this formula to work. So let's plug it in. Our kinetic energy for a rotating object is 1/2 the rotational inertia, which we have here. I'm going to go ahead and write out this number because it's not a super long number. I could leave it as 2 times 10 to the third, and I could plug that in the calculator. But that's 2,000. And then I have my angular velocity here, 0.42 squared. So all you got to do is plug this in the calculator, basically 1,000 times 0.42 squared. And we should get that it has a kinetic energy of 176.4, and because this is kinetic energy, what are the units again? Joules. That says 176, by the way, my handwriting. There we go, and that's it. So we just gotta be careful with the angular velocity. They're usually very often going to give it in revolutions per a set amount of time. We just gotta make sure it's in radians per second. And like I said, paying attention to which variables, which constants they've given us. Let's go ahead and try it one more time. So a physicist whirls a small red ball of mass 0.2 kilograms in a nearly horizontal circle. So going like this. It's kind of like flinging around this way. At the end of a lightweight string, the ball makes 5 revolutions per second. Dang, he's going really fast. How much energy must the physicist supply? So once again, they're asking us to find the kinetic energy he has to create, basically, for this rotating object to cause this motion to occur if the string is 0.3 meters long. So I'm going to go ahead and write out the formula one more time. rotational inertia times angular velocity squared. But let's look at the information we have. Well, we have the mass of the object. We have how many revolutions it goes per second. And we have how long the string is. Remember, that's going to be the distance from the center. If he's swinging it like this, 0.3 meters is the distance from the center. That would swing all the way around. So in this case, we do not immediately get told, here's the rotational inertia. So look back to the notes from the last two slides. We need to expand this formula now to include the formula, excuse me, for rotational inertia. If they don't say, here's the rotational inertia, we now need to plug in that formula as well and kind of go from there. So take a moment to write that out. Okay, so you wrote this out before. It was 1/2. The formula for rotational inertia is mass times, I'm gonna say radius. It means distance from the center, but that's what the radius is. Times angular velocity squared. So we have most of this information. I want you to try this whole question. This is our goal because it says how much energy. That means we just need to plug in everything over here. We have the mass, we have the radius, we know how to get the angular velocity in radians per second. Go ahead and try this whole thing. Okay, so again, I'm going to have 1/2. The mass is 0.20, good to go in kilograms. The radius is 0.3, careful that you squared that. And then I'm going to drop down here and find my angular velocity in radians per second. So I have 5 revs per second. So luckily this isn't going to be much of a conversion because it's already in seconds on the bottom. If I want to get rid of revolutions, I put revolutions in the opposite position and I put what I want to have instead. So there are 2 pi radians for every revolution. So this ends up being 10 pi, but again, we're going to write our answers as decimals. So 10 times pi. So you should have gotten an angular velocity of 31.42, we'll say. That is our angular velocity in radians per second. Okay, so I can go up here now and plug that in, 31.42 squared. So now I just got to plug this all into the calculator. 0.5 times 0.2 times 0.3 squared, be careful with that, times 31.42 squared. Okay, we should get a kinetic energy of 8.88, we'll say, joules. Make sure I did that right. Yeah, with those decimals, that'll happen. Good, that's it. It doesn't have a lot of kinetic energy because the mass is so small. And also that, that string is pretty short. If it were a longer string, notice that gets squared. Yeah, we would have a greater kinetic energy, so not a ton. So I want you to just try it one more time. It's the exact same thing, and we have already also, we have the angular velocity. So how much energy? We are still finding K rotation. Go ahead and try it one more time, keeping in mind that the angular velocity stays the same. Go ahead and try it. Okay, so we have 1/2 mass times r squared times angular velocity squared. And again, we're doing this version of the formula because they don't go, boom, here's the rotational inertia. We need to replace that with the rotational inertia formula. So 1/2, the mass is still the same, which is 0.2. The radius is now 0.6. So what we're going to notice here is how our answer differs. And then we have our angular velocity staying the same. So I just got to plug all this in the calculator. We got 0.5 times 0.2 times 0.6 squared times 31.42 squared. Okay, so now we have 35.54 joules of energy. So again, guys, remember that there's a lot of questions on the AP test that are like this, where they ask, if you were to double this variable, what would happen? Notice that we doubled the R, right? 0.3 to 0.6. But that, our energy did not double, right? 8.88 doubled is not 35 joules, right? That's actually pretty close to being quadrupled. Keep that in mind. If you ever double a variable, that gets squared. What ends up happening is overall, we end up quadrupling our final answer because 2 squared is 4, right? So keep that in mind. It's a really common question. If I double one variable, what ends up happening? Here, because that variable we doubled is squared, then our final answer ends up quadrupled from our original. Okay, real quick, I'm going to grab my charger. Okay, so for this last one, I just wanted to review one more time because, again, in your homework that you're going to do, they say, what is this thing? And you have to be able to look at the formula and know, oh, they're asking me to solve for this variable. So look through your notes real quick. Go ahead and write out what all these different variables are, just so we have kind of a little reference here. And then we'll come back and check. Okay, so this omega, this is angular velocity. So if they say, what's the angular velocity? That's what we're solving for. Don't forget that angular velocity is change in the angle over change in time. Often it starts as revolutions for a certain amount of time. And we have to go to radians per second. So very often that's where it starts from. That's where we get the angular velocity, and then we have to go from there. So if they say, what's the speed or what's the velocity? That's just normal v, right? That's back again in the speed formula that we had yesterday. Make sure we keep those straight. They say just velocity or just speed. That's what they're asking for. I is going to be the rotational inertia. So if they say, what's the rotational inertia? We want I, right? It's possible we don't have to plug in the mass, we don't have to plug in the R, we can just solve for I right away. And then R is the distance from the axis of rotation. You can call it radius. So in your assignment, it's just going to be a matter of solving for different variables. So you have to know, again, what the variables are that we have. You have to know, okay, do I need to plug in the formula for the rotational inertia or can I leave it as is? You'll have to pay close attention to that.